All right, hello everyone, and welcome to our first lesson in Unit 9 for the AP Chemistry curriculum. I will give you a little warning at the beginning of this unit, and that is that we are going to go quite quickly because we are gearing up for our AP Chemistry exam this year. So because we are short on time, I'm going to be doubling and tripling up on lessons so that we can get everything done before the exam. So for our first part of this video, 9.1, we are going to have an introduction to entropy. Our goal here is to identify whether entropy increases or decreases and how big that changes. In general, entropy is going to increase when things start spreading out or having more chaos or having more disorder. So when a substance goes from a solid to a liquid to a gas, particles have more freedom to move and entropy is going to go up. For gases, increasing the volume also increases entropy because particles have more space. And in reactions, if you produce more moles of gas, entropy usually increases. And then finally, entropy is going to increase with temperature because energies become more dispersed among particles. And so overall, the key idea, more space, more motion, more particles, higher energy. So entropy, or S, is really a measure of the different number of possible arrangements, or something called microstates, for a system. Basically, it's how many different ways energy and particles can be arranged. If there are more possible arrangements, the system is more disordered and the entropy is higher. If there are fewer arrangements, it's more ordered and the entropy is lower. So when you see something go from organized to disorganized, like in this image here, that means entropy is increasing. Now for reactions, we calculate entropy change using the idea of comparing the entropy of the products to the reactants. So the equation to remember is delta S, or change in entropy, equals the entropy of the products minus the entropy of the reactants. And if the products are more disordered than the reactants, then delta S will be positive. If they are more ordered than the reactants, then delta S will be negative. In simpler terms, entropy is basically a measure of the disorder in a system. The more chaotic or messy a system is, the higher the entropy. Think about your room. Does it naturally stay clean, or does it tend to get messy over time? Systems naturally move towards more disorder, and that's exactly what entropy describes. From a chemistry perspective, entropy increases when particles have more freedom to move. So when a substance changes state, like from a solid to a liquid or from a liquid to a gas, particles spread out and entropy goes up. And I love this cartoon because it shows how things naturally become more disordered over time. No one has to try to make a mess, it just happens, and that's entropy in action. So big idea here is more disorder, more freedom of movement, higher entropy. All right, now let's look at the clear trend for entropy when discussing different states of matter. So here we can see going from a solid to a liquid to a gas, we are increasing the delta S, or the change in entropy. And that is because when we're looking at this solid, we have very high order, meaning these particles are in a fixed and ordered position. And because of that, they have low disorder or high order, and that's going to be a low entropy value. Then moving to a liquid, our particles still have a finite volume. However, they can now slide past one another and they have a little bit more freedom. And because of that, we are increasing entropy going from a solid to a liquid. Then finally, we get to the gaseous state where we have particles that are completely free and spread out, which is going to be very high disorder or very high entropy. Another really important factor that affects entropy is volume, especially for gases. At a constant temperature, when the volume increases, gas particles have more space to move around. And that means that there are more possible arrangements, So entropy increases and delta S is positive. On the flip side, when volume decreases, particles are squeezed into a smaller space, and that means there are fewer ways to arrange them, so the system becomes more ordered and entropy decreases, making delta S negative. Another key factor that affects entropy is the number of gas particles in a reaction. If a reaction produces more gas molecules, entropy increases because there are more particles moving freely and more possible arrangements, so delta S is positive. If a reaction reduces the number of gas molecules, then entropy is going to decrease since there are fewer particles and less freedom of movement, so delta S would be negative. In this example on the bottom here, we have calcium carbonate breaking down to form calcium oxide and carbon dioxide gas. Since we're going from essentially no gas particles to producing carbon dioxide gas, entropy is clearly increasing because we have more gas particles in this container, which means we have much more disorder, which is going to increase entropy. The last major factor that we're going to talk about for entropy today is temperature. According to kinetic molecular theory, as temperature increases, particles move faster and have more kinetic energy. But more importantly, that energy gets spread out among the particles in more ways. Because this creates a wider distribution of energies, it means that we have more possible arrangements, so we have a higher value of entropy, and that would mean that delta S is positive. You can see on the graph at higher temperatures, the curve on a Maxwell-Boltzmann distribution is going to spread out as we increase temperature, and that is supporting the increasing entropy because now we have more particles at a higher energy, which means we are spreading them out throughout the sample, and that's going to mean more disorder in that sample. So if we were comparing T1 and T2 in this Maxwell-Boltzmann distribution, T2 has a much higher delta S than T1 would. Also notice how entropy increases as we move from solid to liquid to gas, and especially during those phase changes like melting and boiling, where there are big jumps in entropy. So the main trend we want to get from temperature is that as we increase temperature, we are increasing the distribution of energy in that sample, which means we have more disorder, which would be an increase of entropy. And then if we were to decrease temperature, that means we're going to have a smaller distribution of energy, which means more order or less disorder, and that is going to decrease entropy. All right, so now that we have a basic understanding of entropy, I would love for you to pause this video and identify for each of the 4 examples whether we are going to have a positive entropy value or a negative entropy value. So starting out with our first one, we have carbon dioxide solid going to carbon dioxide gas. So here, because the particles are going from a very ordered solid to a much more spread out gas, we are increasing the disorder or increasing entropy. So this means we're going to have a positive entropy value for this reaction. For our next example, we have hydrochloric gas with ammonia gas forming ammonium chloride solid. So as you can see, we have 2 molecules combining to form one solid structure, which means we're going from high disorder with these 2 gas molecules to something a lot more ordered. So because we are decreasing disorder, that means we're going to have a negative value for entropy. For our third example, we have Ag plus aqueous plus Cl minus aqueous forming solid silver chloride. So because dissolved ions are becoming a solid precipitate, the system is becoming more ordered, which means we have a negative value for entropy. And then for our last example on this slide, we have solid calcium carbonate forming calcium oxide and carbon dioxide gas. So because we're going from a solid state to a solid state with a gas, this gas as our product is much more disordered than our original reactant. So because we are increasing this disorder, this is going to be a positive entropy value. All right, let's do a few more examples of that. First one says dissolving ammonium chloride in 1 liter of water. So for this one, we have a solid breaking into ions that can then move freely in solution. So we are increasing our disorder, which means we are going to have a positive entropy value. For our next one, it says mixing silver nitrate and sodium chloride to form a precipitate. In this case, we are taking two aqueous solutions which have pretty high disorder, and we are forming a solid which has very low disorder or high order. So because we're going to something less chaotic, we're going to be decreasing entropy. So this is going to be having a negative value for entropy. Then we have two CH3OH liquids forming gases. So we have a liquid forming two gases, and we know the gaseous state is much more chaotic or disordered than our liquid state. And because we are increasing disorder, that means we are also increasing entropy, so that's going to be a positive value. Then for our fourth example, we have two separate types of gases becoming one gas. Because we are going from a total of 4 moles of gas down to 2 moles of gas, that is going to decrease the disorder, which is going to give us a negative value for entropy. And for the last reaction, where gas reacts to form fewer gas particles, we have a total of 3 moles of gas on the left and 2 moles of gas on the right. Same thing, because we are decreasing our moles of gas, we're going to have a negative value for entropy because we are increasing the order or making it less chaotic. All right, so to wrap up 9.1, let's do one of our College Board questions. Which of the following particle diagrams represents a process during which the entropy of the system increases? So remember, if entropy is increasing, it's becoming more chaotic, meaning there is more disorder. So looking at A, I'm going from a solid to a gas. And I know a solid has very low entropy and a gas is very high entropy. So I am in fact increasing entropy. So this could be an answer. Then moving on to B, I'm going from a gas to a solid. So this is actually increasing order. So this would be a decrease in entropy. Then for C, I'm going to 1, 2, 3, 4, 5, 6 moles of gas to 1, 2, 3, 4 moles of gas. So 6 to 4 means I'm getting more ordered or less chaotic. I have less particles in my substance. So this is going to be decreasing my disorder or decreasing my entropy. And then similarly to option C, we have 1, 2, 3, 4, 5, 6 gas molecules becoming 3. So we're actually decreasing disorder or decreasing entropy. So that would also not be the answer. So the answer for this one was A. All right, now moving into 9.2, this is when we're actually going to be calculating entropy change. So up to this point, we've been predicting whether entropy increases or decreases. Now we're actually going to quantify it using real data. So the key idea is that every substance has a known value called its standard molar entropy, or S, And to find the entropy change for a reaction, we use the formula delta S equals the sum of the entropy of the products minus the sum of the entropy of the reactants. Every substance has something called an absolute entropy value, which is a measure of how much disorder that substance has in a specific state. When a reaction occurs, we're comparing the total entropy of the reactants to the total entropy of the products to see how the system changes. To calculate that change, we're going to use the equation delta S equals the sum of the entropies of the products minus the sum of the entropies of the reactants. So same process that we've done so many other times in different sections. We're going to use the coefficients, multiply them by the value, take the sum of them, and then have products minus reactants. So using the entropy values given for the following substances, calculate the overall entropy of the system below in standard conditions. So we have all of our entropy values here. We also have our chemical equation. So remember, to solve for delta S, it's going to be the sum of your entropy of your products minus the sum of the entropy of your reactants. So first, let's add up our product value. So that's going to be CO, which is 197.7, and H2, which is 130.7. And then for our reactants, we have solid carbon, which is 5.7. And then we have water in a gaseous state, which is 188.8. And that's going to give us 194.5. So now we can take these numbers, products minus reactants. That's going to give us our final answer of positive 133.9. And that's going to be the same unit that we're given, joules per mole times Kelvin. All right, and let's do one more example of that before we move on. This question says the oxidation of PCl3 is represented by the equation above, and the table provides the approximate values of the absolute molar entropies for these substances. Based on the information given, what is the approximate delta S for this reaction? So if we are looking to solve for delta S, remember the equation is delta S equals the sum of your entropies of your products minus the sum of your entropies for your reactants. So for our products, we have 2 POCl3. So I'm going to multiply 2 by our 330, and that is the sum of our products. Now I need to add up all of our reactant values. So we have 2 PCl3s, which are 310, and then we have 102 at 210. So then we're going to solve for that, and that is going to give us negative 170 joules per moles times Kelvin, and that is our approximate delta S for this reaction.